Most people walk right past a glint in the gravel, assuming it's mica or sunlit quartz. Yet in certain bends of slow-moving rivers, that glint signals more than shimmer. It marks a density trap where heavier, potentially valuable minerals settle after seasonal floods. The most common misfortune in rivers isn't lack of material, but lack of pattern recognition. Nature already does the sorting, we simply fail to read it. The misconception that rivers must sparkle with visible gold or gem-grade clarity causes many to overlook less obvious indicators. Most gemstones and heavy minerals don't announce themselves. Instead, they show up as opaque, rounded grains lodged in crevices, often darker or duller than their cut and polished counterparts. Uncut diamonds, for instance, rarely resemble their jewelry store form. They appear as frosted or greasy-looking octahedrons with a faint adamantine luster, easily mistaken for quartz unless you're paying attention to habit and heft. Gold is even more deceptive. Fine placer gold, the kind most rivers offer, often hides under black sands clustering where the current slackens. These pockets form behind boulders at inside bends or where the gradient drops sharply. The real giveaway isn't color but density. When you pan a scoop and find magnetite or ilmenite clumping toward the bottom, you've entered a sorting zone. Most amateurs discard this black sand, unaware that it may carry micronuggets or fine gold flecks invisible until concentrated. Then there are false signals. Shiny mica flakes and weathered quartz can scatter light and mimic metallics. So too can man-made detritus, glass, foil, or industrial slag that lodges in similar sediment traps. But the river is rarely the problem. The real filter lies in observation and testing. If you rely solely on color and surface shine, you'll miss 95% of what's actually valuable. Instead, look for textures. Oily or greasy luster common in diamonds. Rounded but heavy grains, potential garnet or zircon, or layered pebbles that fracture conchoidally, a hint at agate or opal under cortex. The rivers haven't lost their secrets. We've just lost the patience to notice them. But how do you distinguish a random gravel bed from one that's sorted for wealth? That answer lies in the forces that shape a river's inner map. A dull gray rock with no obvious shine often gets tossed aside, yet that same rock might carry more diagnostic weight than a flashy crystal. The key difference lies not in brilliance but in luster type, heft per size, and crystalline habit, all of which offer subtle but reliable cues when examined systematically. Most people chase the wrong signals, seeking shine over structure. But in field identification, the luster's character matters more than intensity. Take luster. While quartz reflects a clean, vitreous sheen, uncut diamonds tend to reflect light in an oily or greasy way, often with less flash and more depth. This difference is minute under sunlight but becomes stark under a jeweler's loupe or angled flashlight. Similarly, moissanite, one of the most common diamond simulants, often exhibits an exaggerated brilliance almost too fiery, which can tip off the trained eye. These nuances matter. In field conditions, even a matte-looking pebble can earn scrutiny if its surfaces reveal conchoidal fractures or uniform curvature, hinting at microcrystalline structure beneath weathering. Heft offers the second silent clue. A seasoned hand quickly notices when a stone feels too heavy for its size. This density intuition builds over time and correlates strongly with material composition. For instance, while quartz clocks in at around 2.65 G/cm3, jadeite hovers between 3.335 and nephrite around 2.930. Diamonds, though small, pack a punch at 3.52. Ilmenite and chromite, both indicator minerals, are even denser. So when panning or scooping, the moment you feel unexpected weight in a rounded grain, especially if magnetism is low, it's worth isolating for further tests. Crystalline habit, the natural geometry of mineral growth, rounds out this triad of indicators. While erosion and tumbling obscure many habits, diamonds still tend toward octahedral or cubic shapes, garnets toward dodecahedrons, and zircon toward short tetragonal prisms. Even smoothed by transport, these shapes leave behind symmetry clues. Moissanite and corundum, sapphire, ruby often retain trigonal patterns that can be faintly detected under magnification. Agate nodules and jasper fragments, though amorphous, betray themselves through color zoning and banding when fractured or lapped. One easy test to validate visual suspicions is the facet doubling check under 10 times magnification. Moissanite, for example, often shows doubled facet edges due to its birefringence, a trait true diamonds lack. Similarly, a flashlight held close to the surface of a suspected opal may reveal play of color or internal diffraction that's invisible in full sun. But there's a catch. Not every river holds stones with these traits. Some yield only rounded quartz, feldspar, and mica fragments, common, light, and valueless. So what causes one river to concentrate weight and geometry while another distributes only debris? The answer lies in the flow history and structure of the watercourse itself. The next topic explores how rivers become natural sluices, sorting treasure from tailings with every seasonal flood. A river doesn't scatter wealth randomly. It organizes it with mechanical precision, driven by flow rate, sediment load, and channel geometry. While casual prospectors pan haphazardly along banks, the real concentrations of gold, diamonds, and heavy stones occur where hydraulic energy drops just enough to let gravity take over. These zones are repeatable, mappable, and when understood, immensely profitable. Start with inside bends. As a river curves, the outer edge cuts deeper and faster while the inner edge slows, encouraging deposition. This deceleration allows dense materials, like gold density ~19.3, garnet ~4, and diamond ~3.5, to settle first, sinking into cracks or layering within heavier gravel beds. These inner bends often hide undercut banks or cobble-rich shelves that retain heavies year after year, even after floods strip lighter debris away. Next are drop zones, places where gradient suddenly decreases, like below waterfalls, rapids, or man-made structures. As the water loses velocity, it dumps its payload. Gold settles first, followed by heavier gem indicators like chromite, magnetite, or even corundum. In these locations, it's not uncommon to find pay streaks, linear zones a few inches wide and several meters long, where placer material has been layered in seasonal pulses. Eddy pockets offer another high-value trap. Behind large boulders or at the downstream edge of islands, water forms slow spiraling zones. These act as natural centrifuges, causing dense particles to spiral inward and settle near the center. Underneath seemingly flat water, a black sand layer might conceal flakes of gold or diamond-bearing gravel, provided the upstream source exists. However, not all heavy concentrations are modern. Some lie buried in ancient riverbeds, paleo-channels, now filled or displaced. These former flow paths, often detectable via satellite imagery or by soil coloration and cobble traces, can carry denser, well-sorted material from a time when river energy and sourcing conditions were different. Some of the richest diamond and gold finds globally come not from current watercourses, but from these ghost flows, preserved under less or volcanic deposits. Field recognition of such zones comes down to pattern literacy. Where are cobbles more rounded and densely packed? Where do black sands persist despite flooding? Are there rust-stained gravels, suggesting iron-rich heavies like magnetite or ilmenite? In some cases, a small trench or pit at the base of an inside bend will reveal cross-bedded gravels with heavy layering at the bottom, a signal that heavier-than-average materials have repeatedly settled there. But not every deposit comes from within the river's current margins. Some sit quietly beside it, elevated, overlooked, and far more ancient. That raises the next question: what happens when the river moves, but the wealth stays behind? The richest clues often lie high and dry, where no one thinks to look above the current river channel stranded by time. These are paleo-channels, ancient riverbeds now perched on hillsides, buried beneath sediment or sliced away by tectonic shifts. While modern prospecting tends to follow water, the old river is where nature did its best sorting, often under very different climatic and geological regimes. Paleo-channels are not always obvious. They can appear as gentle swales, vegetation changes, or cobble-rich terraces far from active flow. In some cases, road cuts or eroded gullies briefly expose their signature: well-rounded, densely packed gravels with fine layering, often cemented by iron oxides. These deposits, sometimes called fossil placers, have been the source of major gold and diamond recoveries in places like California's Sierra Nevada, South Africa's Vaal Basin, and Western Australia's ancient drainage systems. Finding them requires shifting perspective. Instead of chasing water, look for elevation anomalies, gravel beds that make no sense with modern stream flow. Topographic maps and LiDAR imagery help here, revealing sinuous ridges or benches with enough elevation to suggest former channels. In some cases, paleobotany or soil chemistry can provide supporting clues. Darker, loamy soils with high iron and manganese content often overlay these gravels, hinting at prolonged wet periods in the past. Field confirmation demands more than a shovel. Trenching along suspected paleo-channel paths can expose buried pay streaks, but safety and legality come into play. These terraces may sit on private land or require permits to disturb. Once accessed, however, the logic is familiar. Heavies settle at the base of the channel, often just above bedrock or a clay false bottom that blocks further descent. Miners historically called this the bottom run, and it's where gold and dense gemstones tend to accumulate. The composition of these gravels often skews toward denser materials than modern rivers, because lighter sediments have long since eroded away. This leaves behind concentrated black sands, garnet-rich layers, and in rare cases, diamond-bearing rock fragments transported from kimberlite sources long eroded. In jade-producing regions, Ancient fluvial action may have carried nephrite nodules from serpentinite uplands, leaving them scattered among otherwise barren river deposits. The practical challenge is depth. Some paleochannels lie under meters of overburden, accessible only via boreholes or exposed during infrastructure cuts. Others are shallow enough to probe with augers or backhoes. Either way, the costs and rewards are higher. Sampling requires a grid-based approach, with density logging and repeatability across transects before investing in deeper digs or assays. But even with the perfect paleochannel, not every gravel layer is a pay layer. Some are barren. The key lies in internal layering, water-sorted textures, and associated mineral suite. If pyrope, garnet, magnetite, or chromite show up in meaningful ratios, especially alongside black sands, you may be in the right stratum. Yet one more filter remains. Not all gravels, even in ideal settings, yield value. The structure, compaction, and mineral makeup must align. So how can you tell on site whether a gravel zone is worth the labor? The answer lies in how those gravels feel, sound, and sort. The difference between a productive gravel bed and a worthless one can be felt underfoot and heard in the pan before a single test is run. In experienced hands, the sound and feel of pay gravels, compact, coarse, and heavy signal conditions under which heavier minerals naturally accumulate. Most riverbeds contain gravel, but only specific zones display the compaction and texture associated with historical energy sufficient to trap gold and dense stones. Begin with texture. Productive gravels tend to be tightly packed and well-washed with minimal fine sediment. The matrix may feel gritty or resistant when probed with a shovel. This resistance isn't just a nuisance. It indicates historical current strength capable of winnowing away light materials and compacting denser particles. Such gravels often rest above or directly on impermeable barriers, bedrock, hard clay, or even ancient caliche layers, which act as natural riffles, trapping heavies that would otherwise escape downward. Sound is more subtle but no less telling. When panned, productive gravels often produce a distinct click as heavy grains settle and strike the pan base. Black sands, garnet fragments, and even tiny gold flakes accumulate rapidly, producing that characteristic auditory cue of a dense concentrate forming. Light, sandy gravels don't offer this feedback. They wash out silently, their low-density materials swirling without resistance. Coarseness also matters. Gravels rich in rounded cobbles, particularly in a range of sizes from sand to fist-sized rocks, point to high-energy transport systems that once carried heavy minerals alongside them. Uniform fine gravels, by contrast, suggest slower water and poor sorting capacity. The presence of oversized cobbles embedded in finer matrix, often called armored gravels, can be a strong signal. These are the zones where even gold and diamonds can find rest, shielded from scouring flows. But even promising gravels require smart probing. A metal rod or auger can quickly reveal layering, topsoil, loose overburden, then denser packed gravels possibly stained with iron or manganese. When you strike the false bottom, a hard layer beneath which no material sinks, pause and sample above it. This is often where pay streaks concentrate. Whether it's laminated black sand, hematite-coated pebbles, or visibly garnet-rich slices, the signal comes in contrast. Color cues can help too. Yellow-brown iron staining, especially on quartz or cobble undersides, often correlates with long-term water exposure and mineral accumulation. Such patinas form over centuries and can suggest stable deposition zones. In contrast, clean, white cobbles often indicate newer or reworked gravels, less likely to retain value. But compact, promising gravels mean nothing without the presence of indicator minerals. They are the breadcrumb trail leading toward possible gem or metal presence. The next step, then, is to isolate and identify those early signals, small, dense grains whose presence radically increases the odds of a valuable find. It starts as a subtle shimmer in the black sands, a deep red flash, a bronze glint, or a matte black grain too heavy to shift with the swirl. These are indicator minerals, the mineralogical scouts that signal potential for diamond, gold, or gemstone presence nearby. Their role is not decorative. They serve as geological evidence that the forces capable of transporting and concentrating heavies have also been at work on upstream source rock. Most successful finds begin not with discovery of the target mineral, but with correct reading of these silent forerunners. In diamond-bearing terrains, several specific indicators are widely documented and actively used in exploration. Pyrope garnet, with its purple-to-deep red hue and dodecahedral habit, is one of the most trusted. It resists weathering, stands out vividly in concentrate, and is heavy enough density to settle with black sands. Closely followed are chromite and ilmenite, both dense, dark, and occasionally magnetic. While not valuable themselves, their presence strongly correlates with eroded kimberlite or lamprite pipes, the primary hosts for diamonds. Magnetite, though common, still plays a role. It allows for rapid scanning of concentrates using a simple neodymium magnet. If black sands cling tightly to the magnet while a few grains remain unaffected, these outliers are worth inspecting. Non-magnetic high-density grains may include gold, zircon, or even diamond-bearing fragments. Non-magnetic heavies are the elite tier of your concentrate. They're rare, they're persistent, and they demand closer scrutiny. Garnet is particularly useful beyond diamond contexts. Its color and density allow visual isolation, and its survival through transport suggest upstream metamorphic rocks, schist, gneiss, or serpentinite, that may also host jade, corundum, or other durable gemstones. Actinolite, epidote, and greenish amphiboles are often found alongside nephrite jade in serpentinized zones. Their fibrous or bladed forms and slight shimmer in pan concentrate can indicate that you're near a nephrite system, even if no nodules are visible. In gold-bearing zones, hematite and magnetite serve double duty. Their concentration often coincides with the settling of fine gold. Rutile, another heavy mineral, appears as reddish or golden flakes with high luster, hinting at titanium-rich source rocks but also marking zones of high sedimentary sorting, conditions favorable for gold capture. Occasionally, small cubes of pyrite, fool's gold, show up bright and sharp-edged. These aren't entirely useless. Pyrite can accompany gold in certain hard rock systems, but it's essential to distinguish them by their brittleness and lower density, (5 versus gold's (19.3). Zircon is a complicating factor. It's very dense (4.6), often colorless or brown, and can mimic diamond in early stages of recovery. However, it has strong birefringence under a loupe, and when lapped or tested optically, it behaves very differently. Still, its presence in a pan concentrate signals deep crustal source rocks, and that alone can be meaningful. To identify these indicators in the field, use a simple sequence. Pan or sieve to isolate black sands, sweep with a magnet to remove magnetite and ilmenite, then inspect what's left under magnification or good light. If dodecahedral garnet grains, short prismatic zircon, or deep metallic chromite show up in more than trace quantities, you may have a target zone. But indicators only hint, they don't confirm. To move from suspicion to evidence, you need to gather a sample, suite, and test systematically. The next step is building a first-pass workflow that lets you screen promising sites efficiently without investing too heavily up front. The river never stops moving, but your process must. Once indicator minerals appear, the key is not to dig blindly, but to apply a structured, low-cost sampling routine that filters noise from signal. Too many field efforts fail because they skip this step, rushing from glint to guess without confirming that the concentration is repeatable or real. A disciplined first-pass approach using simple tools can reveal whether you're on the edge of a system or just passing through a fluke-rich bend. Start with the basics: a pan, a strong magnet, and 2 nested sieves, ideally 20-0, 85 m and 40-0, 425 m. This size split allows you to isolate both visible coarse indicators and denser finds. Collect material from strategic points, base of inside bends, eddy tails, downstream of obstructions, and critically just above bedrock or hard clay layers. Each sample location should be mapped or flagged for repeatability. Take at least 2 pans per site, one from surface gravels, another from deeper compacted layers if accessible. Work methodically. In the field, concentrate material down to black sands. Use the magnet to separate strongly magnetic grains, magnetite, ilmenite, from the rest. Watch carefully for what stays behind. This residue often contains your best clues: garnets, zircons, chromite, gold flakes, and possibly diamond or corundum fragments. Don't discard anything unusual. Keep this magnetic residue and the non-magnetic remainder in labeled sample bags for later inspection. At this stage, your goal is not to find the diamond or the nugget, it's to identify repeatable anomalies. If 2 or more sites within a small zone yield similar suites of heavies, that's a pattern. If only 1 pan out of 10 shows promise, you're probably on a transient plume. Patterns matter more than individual hits. Keep written notes of color, luster, and density impressions for each location. Later, these notes become the framework for higher investment decisions. Use weight in hand as a supplementary test. Isolated grains that feel oddly heavy when dry or click sharply against a metal spoon or dish deserve extra scrutiny. Run simple scratch tests using quartz hardness (7), corundum sandpaper (9), or glass (5). For instance, garnets will scratch glass but not quartz. Jadeite and nephrite will often scratch neither, but resist abrasion from steel. Field UV lights are optional at this stage but can add value, especially for diamonds' bluish fluorescence and some zircon's yellow or orange glow. However, UV results are not definitive. They should only guide closer inspection. If something fluoresces unexpectedly, it should go into the test further pile. Photography helps. Take close-up images of promising concentrates against scale grids like a coin or ruler. Not only does this allow later comparison under better lighting, but it also builds visual memory for spotting these traits faster next time. In many field studies, especially in remote areas, photographs and GPS logs become more valuable than the samples themselves when mapping repeat patterns. But even this process, efficient as it is, can lead you astray. Certain minerals mimic everything, from gold to garnet to diamond, with uncanny visual accuracy. The next challenge is learning how to catch the fakes before they cost you time, hope, or worse, money. Every serious prospector eventually encounters a heart-sinking moment. A bright crystal or metallic fleck, isolated and promising, turns out to be a convincing imposter. The field is littered with false positives, minerals that look like the real prize but fail under scrutiny. Recognizing and eliminating these early not only saves time, but protects against wasted lab fees and misdirected effort. Knowing how to unmask these imposters in the field is as critical as spotting the real thing. Begin with zircon, one of the most common diamond lookalikes in river sediments. Transparent to translucent, it appears as small, brownish to clear prismatic grains with a noticeable luster. In certain lighting, especially under UV, some zircon fluoresces, adding to the confusion. Its density is close to that of diamond (4, 6 versus 3.5), and it resists weathering, making it a frequent fluvial survivor. But under magnification, zircon often reveals rounded terminations and strong double refraction. Its inner edges appear blurred or doubled when viewed through a loupe. A true diamond will appear crisp, with no doubling. Moissanite, another notorious impersonator, is harder to identify in rough form but can deceive thermal testers, giving false diamond readings. However, moissanite conducts electricity, a key difference. A basic conductivity meter can flag this discrepancy on site. Moissanite also shows birefringence under magnification, a trait true diamonds lack. If you spot double facet lines or rainbow light distortion, it's likely moissanite. Corundum, ruby, and sapphire in gem form also presents as rounded, opaque to translucent grains with high hardness (9). While valuable in its own right, it's often mistaken for low-grade garnet or overlooked entirely due to its dull surface when weathered. A quick scratch test can distinguish it. Corundum scratches quartz and glass with ease, whereas most garnets will stop at quartz or scratch it weakly. Importantly, corundum is not magnetic and is often found with spinel or kyanite in metamorphic terrains, so its context offers clues. Then there's the classic fool's gold pyrite. Bright metallic and often cubic, it's mistaken for gold by nearly every newcomer. The giveaway lies in its brittleness. Gold bends, pyrite shatters. Drop either on a hard surface, gold will dent or flatten slightly, pyrite will chip or fracture. Density is another check. Gold is far heavier, 19.3, than pyrite 5, and a pan test shows this clearly. Real gold stays down even in heavy agitation, while pyrite will dance in the upper sands. Glass and high-index simulants, especially in streams near urban or mining areas, pose another problem. Broken bottle fragments smoothed by years in the river can resemble clear quartz or even topaz. These lack crystal habit and will show conchoidal fractures with smooth, shell-like edges. They can also scratch glass, but tend to shatter when struck. Their lack of density and optical deadness under magnification makes them easier to rule out after a second look. A single promising sample means little without repeatability. The real power comes from discovering a pattern, where nature has not just deposited a fluke grain or two, but actively concentrated valuable materials over time. This requires a shift from random scooping to structured grid sampling, a discipline few apply in casual prospecting. But those who do often uncover stable deposits others miss entirely. Grid sampling in fluvial environments begins with spacing. Choose a section of river, perhaps 30 to 50 meters long, and divide it into 3 to 5 meter segments. At each grid point, take consistent depth samples, ideally from multiple stratigraphic levels, surface gravels, mid-layer, and just above bedrock or clay base. Each layer represents different depositional energy and time. Label and record each by GPS or marked stake. For every sample, run identical concentration procedures. Sieve to 20 and 40, pan to black sand, remove magnetic fractions and isolate non-magnetic heavies. Consistency is critical, don't mix layers or skip magnet separation. Only through repeatable processing can you detect meaningful trends in mineral presence and density. The goal is not just to find gold or gemstones, but to build a map of indicator distribution. Are pyrope garnets clustering in the downstream half? Is chromite consistently found near a side channel? Are gold flakes only showing up at the lowest layer of gravel near the bend apex? These spatial patterns suggest concentration zones, places where long-term deposition has sorted material mechanically. Track concentration by estimating heavies per pan. How many garnets, gold specks, or dense grains remain after full washdown? A grid square yielding 8-10 garnet grains per pan repeatedly may be within the gravity drop zone of a larger upstream source. Compare this to areas where only 1-2 grains appear or none. This ratio helps you prioritize future digs or refine your grid spacing. Documentation matters. Many prospectors lose track of their best zones simply by not recording results tightly. Use waterproof field logs or voice notes transcribed later. Photograph each sample's final concentrate next to a ruler or standard object for later review. This visual record, coupled with spatial coordinates, becomes your personal prospecting database, a powerful asset if you return in different seasons or after floods. But grids do more than reveal positive patterns, they expose negative zones too. Areas with poor concentration can be safely ruled out, saving future effort. When a section yields clean quartz and light gravel 3 layers down with no black sand or indicators, you've learned something valuable. Don't dig there. The efficiency gain alone is worth days of test panning elsewhere. Eventually, one or more grid squares will stand out, not just for having interesting grains, but for showing layered conformation. Multiple heavy indicators in close proximity in multiple layers across more than one pass. That's when deeper investigation becomes justified. But what should trigger higher investment, like assays or lab testing? Not every promising site warrants it. The answer lies in matching field signals to known thresholds of economic value. Even promising sites can waste resources if testing escalates too soon. The difference between a scientific prospect and a hopeful hunch lies in hitting the right thresholds: measurable, observable, and justifiable. Before sending samples to a lab or investing in heavier equipment, you need confirmation that the material shows multiple independent signals aligning with known mineral system behavior. The visual alone can't carry the weight. It needs backup from physical, thermal, and density tests that expose what lies beneath the surface. Start with simple optics. A rough stone's luster, how it reflects light, is a deceptively powerful diagnostic. Diamonds show greasy to adamantine luster, often appearing dull or oily when dry, but lighting up under angled LED or natural side light. By contrast, quartz and glass tend toward vitreous or shiny reflections with shallower surface depth. This subtle shift becomes clearer after a light rinse and drying the sample thoroughly. A true test: under a strong light, rotate the stone slowly. Does the light appear to enter and bounce back from within or skate across the surface? The latter is common glass or quartz, the former may suggest denser, higher index material. Translucency is another variable often misread. Nephrite jade, for example, can appear opaque in thick nodules but transmit light at thin edges when sliced or naturally broken. Agate or chalcedony may reveal banding or color zoning when wet, evidence of cryptocrystalline silica, a sign of slow geologic formation under specific chemical conditions. Even jasper, often overlooked, carries diagnostic color zones and fracture behavior. Conchoidal breakage, matte surface, and high heft signal potential for cuttable material. But these visual clues must be matched with physical performance. Thermal conductivity testers, affordable and handheld, quickly eliminate most simulants from diamond candidates. True diamonds dissipate heat instantly and register on these testers in seconds. However, moissanite can fool them, so you must also run electrical conductivity. Diamonds are insulators, moissanite often conducts. A sample that passes thermal but fails electrical, likely a synthetic or lab-grown imposter. Not all rivers can yield value, no matter how meticulous your sampling. The geology beneath the flow determines whether heavy minerals, gemstones, or placer gold are even possible. And while the romantic notion persists that any stream might hide riches, reality draws clear boundaries. Understanding these regional filters isn't just academic. It spares you months of wasted effort chasing clues that were never geologically viable to begin with. Begin with tectonic context. Diamonds almost exclusively originate in kimberlite or lamproite pipes, volcanic structures rooted deep in the mantle. These pipes are ancient, and only a few are known to have transported diamonds to the surface. If your river isn't downstream from one of these structures, your odds of finding natural diamond, regardless of indicators, are essentially zero. In places like northern Canada, Botswana, Russia's Yakutia, or Australia's Argyll region, river gravels may indeed hold diamond-bearing material, but only because active erosion is releasing those stones from already known pipes. Similarly, jade doesn't occur just anywhere. Nephrite is typically associated with serpentinized ultramafic rocks, regions where tectonic plates collided and altered the mantle rocks near the surface. These zones often contain actinolite, tremolite, and other amphiboles, which metamorphose into nephrite under high pressure. Key nephrite regions include British Columbia, New Zealand, parts of Central Asia, and Siberia. If your stream isn't cutting through serpentinite belts or sheared ultramafic terrains, the odds of finding jade are minimal. Jadeite, on the other hand, forms in subduction zone terrains, especially where blueschist and eclogite facies rocks occur. These conditions are rarer still. Guatemala and Myanmar are classic jadeite zones for a reason. They sit atop major tectonic sutures. Unless your river cuts through these unusual metamorphic zones, jadeite will not appear, regardless of visual similarities. Gold has wider distribution but is still far from universal. Its primary source is hydrothermal veins, especially those formed near faults or shear zones where quartz and sulfide minerals precipitate from mineral-rich fluids. These veins weather and release gold into streams, creating placer deposits. Key global regions include the western US, parts of Alaska, much of the Andes, Central Africa, the Urals, and parts of Australia. Without upstream hard rock sources or older paleoplacer systems, a river is unlikely to accumulate meaningful gold content. Black sands alone are not proof. Even agate, jasper, and opal require specific host rocks. Agate and jasper derive from silica-saturated hydrothermal fluids, often in volcanic contexts. You'll find them in basalt flows, rhyolite zones, or silicified sedimentary units. Opal needs volcanic ash or deeply weathered tuff beds with sufficient silica leaching and a slow enough water table to allow for precipitation. This is why Ethiopia, Australia, and Nevada yield quality opal conditions align. In contrast, rivers in granitic terrain may offer quartz and feldspar aplenty, but little of gem or heavy metal value. Similarly, rivers draining sedimentary basins often yield little more than sandstone and shale fragments unless ancient placer systems are preserved. To judge a river's potential, begin with regional geological maps. Look for proximity to known pipe systems, metamorphic belts, or gold-bearing shear zones. Cross-reference with historical mining records or mineral survey data. If there's no mention of mineralization in 100 km, your odds drop dramatically. Still, exceptions occur. Some rivers slice through relic deposits like paleochannels buried under newer sediment. Others may cut into old tailings or glacial till, reworking older material into fresh concentrates. But these are the exception, not the rule. So once you've filtered your terrain and tested your indicators, it's time to get specific. How do you adapt your method to the exact material you're hoping to find, be it diamond, jade, opal, or agate? Each has its own field logic, and the smarter your toolkit, the sharper your yield. What you seek dictates how you search. While rivers can carry many heavy or durable minerals, each target diamond, jade, opal, or agate requires a tailored approach in both fieldwork and identification. The indicator suite, host rock context, and concentration behavior all differ subtly but significantly. Fail to adapt your method, and even rich deposits can appear barren. For diamonds, the most consistent logic begins with mineral proxies. Pyrope garnet, chrome diopside, chromite, and ilmenite occur in kimberlite weathering halos and survive transport better than diamonds themselves. Sampling near known or suspected kimberlite pipes, especially in glacially reworked terrains, requires fine mesh sieves 40 or finer and magnetic separation. Grains are typically sub-millimeter, rounded, and often stained. Confirmatory steps include refractive index under a microscope or thermal conductivity for larger grains. In fluvial contexts, search downstream of known pipe-bearing terrain and focus on areas where erosion cuts through ancient volcaniclastic sequences. Nephrite jade, in contrast, behaves like a boulder. It resists abrasion, weathers slowly, and concentrates in coarse cobble bars rather than fines. The best signals come from proximity to serpentinized ultramafic belts, where watercourses intersect with talc schist or actinolite-bearing zones. Here you're looking for dense greenish-gray boulders with a waxy surface or fibrous fracture. Tap test, nephrite produces a dull thunk when struck, not a ring. Scratch tests help too. Jade resists steel but not diamond files and rarely shows granular fracture. Look in stream beds where large stones accumulate, especially on the inside curve of alpine creeks. Jadeite is harder to find and verify in the field due to its high-pressure origin and similar appearance to quartz or felsite. It's denser, Sg-3335, sometimes more vividly colored apple green, lavender, and breaks with smoother, tighter fracture than quartz. Key signs include association with blueschist, omphacite, or glaucophane minerals, often in high-grade metamorphic river zones. Because jadeite boulders often retain weathered crusts, test break small pieces to expose internal luster. Under polarized light, jadeite shows bright interference colors, a field sign if thin slivers can be cut. Opal plays by different rules. It's hydrous, fragile, and forms via silica gel deposition in volcanic or sedimentary cavities. In rivers, common opal appears as light-colored nodules or vein-like fragments with conchoidal fracture and waxy luster. Precious opal shows play of color, but only when kept moist or polished. Most opal indicators lie upstream, silicified ash beds, weathered tuffs, or rhyolite domes. If your gravel samples contain glassy, low-density, translucent pebbles with no sharp crystal habit, test for fracture and water absorption. A UV flashlight may reveal faint green or white fluorescence, but it's not diagnostic. Cut and polish remains the only real field check. Agate and jasper are more forgiving and widespread. They form through slow silica deposition in volcanic voids or as replacements in fossil beds. In river contexts, they appear as banded nodules or opaque red-brown stones with fine-grained texture. Jasper resists fracture and often breaks with clean edges, whereas agate shows concentric banding and translucency. Look for nodules that appear cracked but not crumbled, with color zoning underwater. These gravels tend to be heavy, smooth, and subtly patterned even when dry. The best collecting spots are where eroded basalt flows meet water erosion, especially alongside channels or cut banks. Each material demands a different eye and toolkit. A pan that works for gold won't reveal jade. A magnet won't help with opal. Your search must match your goal, but even when you know what to look for, timing can make or break your effort. Flood seasons can bury deposits, permits may restrict access, slopes may become deadly after rain. The field offers value only to those who respect its rhythms and its risks. The next essential element is recognizing how environmental and legal constraints shape the real-world search. A verified find doesn't mean a valuable one, not until it's placed within the market's unforgiving framework of clarity, size, color, and origin. Many field-collected stones and concentrates test genuine, but fall short in value because they lack the traits buyers pay premiums for. The harsh reality is that natural doesn't mean profitable. To cross that line, your material must enter the trade classification system, the grading structures that dictate how rough stones and placer gold convert into cash, partners, or cutting contracts. For placer gold, value is calculated by weight and purity, measured in carats. 24K equals pure gold, or fineness, e.g., 0.965 equals 96.5% gold. Raw gold from rivers often tests between 80–95% purity, with the rest composed of silver and trace metals. A gram of 90% pure placer might fetch spot price minus 5–10% at a refinery due to handling loss and assay uncertainty. For a market price of $60 gram, this translates to roughly $50–55 if sold raw. Coarser flakes and nuggets attract higher premiums, sometimes 10–20% over spot, especially if natural, unaltered shapes are retained. Finer gold under 100 mesh is harder to recover and sells at discount due to smelting difficulty. For gemstones, the value curve sharpens dramatically. Rough garnet, for instance, may be worthless unless transparent, large, and clean. Pyrope or almandine fragments, even vivid red ones, are often industrial grade, worth less than $1 per kilogram. But a single facetable garnet over 10 with clarity and saturation can cross 5,200 depending on species. The same is true of spinel, zircon, and corundum. Most rough is too flawed, too small, or too fractured to cut profitably. Buyers look for three minimums: size, often 3+ carats rough, structural integrity, no cleaving planes, and optical orientation. Without these, material is rejected outright. Jade, however, operates differently. Both nephrite and jadeite are judged not by transparency alone, but by texture, grain, uniformity, and color. For nephrite, the highest values up to 5,000/kg come from mutton fat white jade with buttery translucency and even color. Common green or black nephrite sells for $10–150/kg depending on polishability and demand. For jadeite, color drives value. vivid imperial green, lavender, or ice jade, colorless, translucent command huge premiums if uniform. Even small boulders of gem-grade jadeite can exceed $100,000 per piece. But mottled or coarse-grained material, no matter how real, may fetch under $100. Opal is even more volatile. Common opal without play of color may sell for under 10/kg. But precious opal with intense, stable play of color, especially in red and blue patterns, can range from $100 to $5,000 per carat depending on size and base color. Rough must be tested for stability, some cracks easily or crazes as it dries. To assess this, stones are left to dry in ambient air for days and then re-examined. Cracking equals zero value. Only those with strong color, no matrix interference, and minimal cracking proceed to cutting. Agate and jasper, while common, still hold niche value. Large, vividly banded agates, especially with fortification patterns or unique inclusions like plume or moss, can sell for $20-200 per piece to collectors. High-contrast jasper, especially in orbicular or scenic patterns, commands up to 10/lb in slab form. But uncut, non-figured stones rarely exceed decorative pricing unless regionally branded, e.g., Montana agate, Mukate, ocean jasper. Market channels matter. Selling directly to end users via gem shows, online auctions, or specialty forums brings highest returns but requires grading knowledge, marketing skill, and trust building. Selling rough to cutters, on the other hand, means lower prices but faster sales. Most rough is sold to intermediaries, not end users. These buyers demand clear documentation: GPS origin for jade or opal, SG hardness, refractive index if tested, and size carat metrics. But value is only part of the equation. Knowing the potential worth of your find also helps avoid exploitation. Too often, underpricing traps or premature sales strip prospectors of their share. To guard against this, one must also understand how fraud, mislabeling, and lowball offers skew the true worth of raw field material. That's where we turn next: how to spot and avoid the traps that cost you the payoff.